Hello everyone. So welcome back to the series on Introduction to Biostatistics. So I'm sorry that I have not done a lot of lectures these days. So we'll continue our lectures today. And I want to continue the lectures in such a way that we are going to do all the lectures back again from the start. So I want to update and refresh the lecture set. So the first chapter is going to be Introduction to Biostatistics. So we have already done this, but let's go back and revisit the introduction to biostatistics. So what are our learning objectives? So first we'll define the key terms. So we'll start defining statistics. What is biostatistics? What is a variable? What's a population? A sample? And then we'll try to distinguish between two types of variables, quantitative and qualitative, and we'll also try to distinguish among the quantitative, the discrete and continuous variables. So we will also try to identify the four scales of measurement, so which is the nominal, ordinal, interval, and the ratio. So if somebody is familiar with noir, which is black in French, so it's an easy way to remember the four scales of measurement. And we can also try and understand the different sampling methods, the simple random sampling, systematic sampling, and the stratified sampling. So in this particular lecture, we are only focusing on the probabilistic sampling methods. So I'll give you a key overview of the main probabilistic sampling methods, and we'll also go through some non-probabilistic sampling methods in the coming lectures. So, and at the end, we'll discuss the scientific method and mainly the difference between accuracy and precision. So let's go to the first topic, which is introduction. So what is the introduction mainly on? We'll start with the two main ones, which is data. So what is data? So data is the raw material of statistics. So we simply define data as numbers. So these data generally can be, for example, from measurement. So this can be, for example, say if you're measuring the weight of a patient, for example. This can also result from, for example, counting. So which can be an example from say for example how many patients have been discharged or how many patients have been admitted in the lectures. So all of that, and we'll continue into statistics. So what is statistics? So statistics is a field of study that is mainly concerned with the collection, organization, summarization, and the analysis of data. So what do we do once we collect, organize, summarize, and analyze the data? Is we try to draw some or make some decisions, which is what is written here as drawing inferences. So drawing inferences is basically making decisions from the data. So we make decisions from the data. So when only a part of the data is being observed. So the reason for this is, say for example, we take a population. So what do we do with the population? So we want to make some decisions for the population. So say for example, you want to know whether a drug is particularly effective on a population. So among the population, we take a tiny sample. So think of it like taking a slice out of a pizza. So think of this as the sample. So say for example, I'm going to have this sample right here, right? So this sample right here. Now from the sample, what I'm going to do is I want to test all my observations on this particular sample. So say for example, if I'm doing a test on the sample, if I want to find out whether a particular drug works effectively or not, so I'm gonna do it on a particular sample. Then once you do it on a sample, the generalization is that you're basically inferring that how the drug works on the sample will also work similarly on the population. So that is why when we say the word drawing inferences, so this is what we mean. So inferential statistics, mainly we will discuss the concept of hypothesis testing, estimation, all of those. So let's get into biostatistics. So what is biostatistics? So there are tools of these statistics that we use are generally employed in many fields. So you can go into business statistics, economic statistics, and agricultural statistics. So the one that we are mainly concerned about is biostatistics. So this is the term that is used when the data analyzed are derived from biological sciences and medicine. So the focus is on medicine. So if you use both biostatistics, whenever you use the term biostatistics, we talk about biological sciences and medicine. If you're only focusing on medicine, then that field of statistics or biostatistics is called clinical biostatistics. So just remember that when we use just for broad scope biological sciences, that is generally called basic biostatistics or biostatistics, and when you're focusing on medicine, we call this clinical biostatistics. So the goal of biostatistics is to investigate and evaluate the nature and meaning of information that is contained in biological data. So here we are focusing mainly on what any type of biological data and trying to draw inferences from this particular information that we obtain. So what are the different sources of data? So where do we get our data? So in biostatistics, there are 4 different sources which you get data from. So the first one is the routinely kept records. So these can be hospital charts, birth or death registries. All of these can be considered routinely kept records. So for example, even electronic health records are an example of routinely kept records. The second one are surveys. These are used when data is not available in records. For example, things like patient satisfaction. So say you want to find out whether you want to improve the emergency department or how to improve the emergency department. So you could always take patient surveys and find out, what kind of information or what kind of a doctor or what kind of a service would be more appropriate for the patients. So the third are experiments. So this is more commonly what we use as trials. So these are control studies. We generally to test specific strategies. So for example, things like drug efficacy. And we are also going to use some external sources as well for different sources of data. So these can be from published reports, data banks, and other scientific literature. So these are the common sources of data in biostatistics. So next definition is variable. So what is a variable? So a variable, the name itself says that it is something that varies. So variables is a characteristic that takes on different values in different persons, places, or things. So for example, if you take a particular variable, right, this is something that is specifically characteristic, but it changes with a particular person, place, or thing. So things like, for example, in biostatistics, the diastolic blood pressure, heart rate, the height of adult males, and the weight of preschool children. So all of these are examples of different variables. So what are the different types of variables? So the first type of variable, which is the most common, is called as the quantitative variable. So this is measured in the usual sense, which means we measure it using a measuring instrument. So this conveys information regarding the amount of a particular thing. For example, say height, weight, age, all of these are examples of quantitative variables. So these can also be one different characteristic from qualitative is that quantitative variables can be subject to arithmetic operations. So for example, things like averaging, taking a median, right? So taking a variance, for example, all the statistical operations that we generally perform can be subjected on quantitative variables. So we also have the other type, which is the qualitative. So the name itself says quality. So these are characteristics that are categorized. So meaning that this measures consists of categorizing. So they convey information based on attributes. So this can be examples like ethnic group, diagnosis, gender. So the analysis often here involves counting the frequencies of these particular categories. So the next one are random variables. So what are random variables? So values that arise as a result of chance factors and values that cannot be predicted in advance are generally called random variables. So for example, the adult height of a person is usually the result of the genetics, the environment, and for example, sometimes it can be the diet as well, right? So all of these values are something that can be result of chance factor. So you cannot predict the values in advance whether a particular person will be of a particular height after a particular time. So the values that result from measurement are generally called observations or measurements. So these variables are generally the ones where there is the random assignment is generally called random variable. So as we discussed the random variables, we have two types of random variables. We have the discrete random variables and we have the continuous random variables. So what are discrete random variables? So discrete random variables, the name itself says discrete, which basically means these are separate from one another. So what do we mean by separation here is that these are characterized by gaps or interruptions in the values that it can assume. So most often discrete random variables are generally result from counting. For example, things like the number of daily admissions to a hospital, or the number of patients coming for a particular surgery to a hospital, or if you're going to the dentist, the number of decayed, missed or filled teeth. So things like, for example, if you take the number of admissions, there cannot be 1.5 or 2.99 admissions because these values are generally result from measurement. So when you count, you're always counting in whole numbers. So when we do the counting here, we always assume the discrete random variable. So we can analogize to this. So the analog for this is to assume that this is to be a step. For example, if you're counting the number of steps, so there is no 2.5 steps. So as it moves on, there is discrete number of steps. So the next type is the continuous random variable. So continuous random variables do not possess any gaps and they can assume any value within a specified interval. So these are usually result from measuring. So things like height, weight, skull circumference, all of these are examples of continuous random variables. So these are mainly limited by the instruments because the accuracy of the instrument forces us to record these values as discrete values because we always round these values based on the precision or the sensitivity of that particular instrument. So a continuous random variable is usually assumed to be a straight line, something like this, for example. So which means there is no steps that stopping them. So for example, if this is 1 and if this is 2, so there is a value that can exist which can be 1, for example, 1.9945. So here the level to which that you can measure is only limited by the sensitivity of the particular instrument that we are using to measure, right? So sensitivity of the instrument. So this is the one that limits us from measuring a particular value. So in terms of the hierarchy, so we classify variables into two types. We have the quantitative and the qualitative variable. So the quantitative measures the amount while the qualitative measures the attribute. So quantitative variables can be classified into two subtypes again. We have the continuous variables and the discrete variables. So continuous variables are the results of measurements. Discrete variables are the result of count. So now let's move on to the population. So population is generally considered as the largest collection of entities for which we have an interest at a particular time. So for example, if you're doing a particular study and if your population is generally determined by the sphere of interest or what we generally call what is it that your focus is. So what is the focus of the study determines what your population is. So for example, if you want to calculate the survival rates of patients in a particular hospital suffering from a particular disease, then all the patients that come to the hospital for that particular disease at that particular time are generally considered as the focus because you cannot reliably take in all of the population. So we can only assume that some of the population will always be. So we only take in the entire population at interest, so which is going to be our focus. So we can classify population into two types. We have the finite population, which generally consists of a fixed number of values, and infinite population, which is the endless succession of values. So for example, if you're trying to calculate the mortality rate at a particular hospital, so the chances are the values are going to be continuously changing every day because every day there's going to be a patient, for example, that might be suffering from a particular disease which can who can succumb to death. So those are considered infinite population. So that is why whenever our sphere of interest, whatever our sphere of interest is, that particular population is there. So that is what determines our population for that particular study. So what is a sample? So a sample is simply a part of the population. So we generally analyze samples to draw inferences from the about the population. So the main reason we take a sample is because it is often physically or economically impossible to measure the entire population. So for example, even governments, when they do a census, they might be, for example, 80% full or 90% full or 98% full. So it's very hard to achieve that 100% because it's not possible to take the values from the entirety of the population. So how do we do when we want to visualize? So in terms of visualization, so if you take the entire blue circle to represent the population, so population generally referred to with an uppercase N. So the orange dots here are represented as the sample here, so which is the smaller case n. So from the sample, we draw an inference. So which is basically we make a decision based on the study that we conduct on the sample, and then we apply that decision onto the population itself. So which is basically saying that, for example, say if you want to calculate the average height of the population in a particular country. So rather than taking the average height of every person in that country, we take that for a particular sample, and then once we have the data for a particular sample, we can estimate that this is going to be the average data or average height of the population entirely. So that is one way of thinking about inference. So the next one is measurement. So measurement, the assignment of numbers to objects or events according to a given set of rules is generally called measurement. So the scales of measurement generally depends on the rules that are used. This is critical because this particular scale determines what statistical tests are valid for a particular scales of measurement. So there are 4 scales of measurement which we abbreviate using the pseudonym noir. So which is the French for black, right? So noir represents N, O, I, and R. N representing nominal, O representing ordinal, I representing interval, and R representing ratio. So that is where we get the NOVA. So the first one out of them is the nominal scale of measurement, which is the lowest level of measurement, most often referred to as the categorization scale, which is we generally name these observations and we classify them into mutually exclusive and collectively exhaustive categories, which means that you can either be in one category or the other category. You cannot be in one or more than one. So for example, things like male and female, the blood type, well or sick, all of these. So the mathematical operations that can be performed are usually only counting. So that's the only thing that we can do with nominal scale. So the second one is the ordinal scale of measurements. So ordinal scale, the observations are generally ranked or ordered. So one category is usually higher or more than the other, but this hierarchy is not clearly defined. So the hierarchy that is present is not clearly defined. So what do we mean by this? For example, take the example of the severity of illness. So the difference between improved and much improved is not clearly understood as the same as the difference between unimproved and improved. So if these differences are the same, then the hierarchy is clearly defined. So here, because of this, the hierarchy is not clearly defined. So this results in a situation where even though we know that the severity of illness, if somebody says it's much improved, it's also greater than improved, but it's not clearly how evident how much has it improved. Okay, so that is why we can say that the distance between these categories is not necessarily equal. So socioeconomic status, the same thing here again, low, medium, and high. So if we do not know whether the difference between medium and high is the same as the difference between low and medium. So this is the ordinal scale of measurement. So the third is the interval scale of measurement. So this is possible to order measurements, and here the hierarchy is well defined. So the hierarchy is well defined. So because the hierarchy is well defined, so we can say that the distance between any two measurements is always known, and this uses a unit distance and an arbitrary 0 point. Now here the 0 is not the true absence of the quantity, but rather the value that can emerge from a particular value. So things like temperature, for example, degree Fahrenheit or degree centigrade. So 0 degree centigrade does not mean that there's no heat. It generally means that it's a value on the scale of a measurement. So here the one flaw is there is no clearly defined absolute 0. So absolute 0 meaning the absence of a particular value. And the last one, which is the highest level of measurement, is generally characterized by a true 0 point, which means when you say a particular value is 0 as a ratio on the ratio scale, It basically means that the value is includes the whatever the quantity that we are measuring is totally absent. So the equality of ratios can be determined. So things like height, weight, length. So if you have a person weighing 200 pounds is twice as heavy as a person that weighs 100 pounds. So these are all examples of ratio scales. So that is why ratio scales are the highest level of measurement. So in a figurative way, we can write down the amount of information content that we get from a particular scale of data. So when we want to visualize these measurement scales, so the nominal scale is names or labels. If you add order to that, it becomes ordinal. If you add equal distance to the ordinal scale, we get interval scale. And if you add true zero to the interval scale, we end up with ratio scale. So that is why nominal scale is the lowest amount of information, while the interval and ratio scale, so the ratio scale becomes the highest amount of information. Most often, nominal and ordinal scale are most often used for qualitative variables. Interval and ratio scale, because these are inherently numerical, so they generally have to be a quantitative scale. So this is the difference here. So the next is the concept of statistical inference. So what is statistical inference? So statistical inference is the procedure by which we reach a conclusion about a population on the basis of the information that is contained in a sample. So this requires a scientific sample. So the simplest form of what we call a scientific sample is called as a simple random sample. So non-scientific samples, why do we not use them? So non-scientific samples are all generally called convenience samples. They can lead to bias, which means it can lead to errors in our judgment or errors in inference. So let's start with the different types of sampling. So we start with simple random sampling. So what is happening in a simple random sampling? So for example, if you have a sample of size n that is being drawn from a population of size n, then whatever amount of samples that are whatever is the total population, each possible sample n has the same chance of being selected. So for example, let's say if you have 100 people inside the population, and let's say you're selecting 10 for the sample, each person inside the population has the same chance of being selected for the sample. So that is what we call the simple random sample. So there are two types of simple random sampling. So sampling with replacement, which is where the member is returned to the population after being selected. So sampling without replacement is where member is not returned. So once you're selected, you're not put back into the population. So that is why with replacement and without replacement. So we generally use random number tables or computer generation to do simple random sampling. So the next one is systematic sampling. So this is generally used when records are stored systematically. For example, if you have the entire list of patients in a particular hospital, then we can use them to systematically select the number of samples that we need. So to do that, we generally have to calculate the sampling interval, which is the value k. So k is the size of the population divided by the size of the sample. So once we have the the k value, what do? Is we select any random starting point between 1 and k. So for example, if the k is 10, we are going to choose any number between 1 and 10. And then you are going to calculate every kth item before thereafter. For example, let's say if the k value, so let's say we start randomly at 2. And let's say that the k value is 3. So if the k is 3, we are going to choose any random number between 1 to 3. So for example, 1, 2, and 3. So we're going to select one of these random numbers. Let's say if I select 2. So then if I select 2, the next sample is found by adding 3 to the selected number. So which gives us 5. And then I'm going to add 3 to this again, which gives me the next number 8. Again, I'm going to add 3 to this, which gives me 11, and so on until the desirable sample size is reached. So this is how we can visualize the systematic sampling. So the next one is stratified random sampling. So this is used when the population is partitioned into groups or strata. So units within a stratum are similar to each other regarding the variable of interest. So what do we do first is we identify the strata, which is what are the different groups that are present. For example, is it age groups or is it trauma levels? And from there, we draw a random sample independently from each stratum. So what does this do is it increases precision by handling the variability between the subgroups, which is basically saying that it can help us with making sure that it's uniformly distributed. So all the samples are uniformly coming from all parts of all subgroups that are present in a particular population. For example, we have stratum A and stratum B, right? I need 3 people from stratum A and 3 people from stratum B. So what I'll do is I'll take stratum A, randomly select 3 out of them, and then stratum B, randomly select 3 out of them. So this is how we visualize the stratified sampling. So these are the 3 probability sampling methods. So the 3 of them that we have discussed are simple random sampling, stratified sampling, and systematic sampling. So now let's go to the last one, which is the scientific method. So why is the scientific method important? So scientific method is what we use to identify information or to find knowledge. So the definition of the scientific method is the process by which scientific information is collected, analyzed, and reported to produce unbiased results. So there are 4 steps in the scientific method: observation, which is identifying a phenomenon; hypothesis, which we formulate a prediction; experiment, where we design a study to test the hypothesis; and conclusion is where we analyze the data to accept or reject the hypothesis. So there are 2 places where we generally need the scientific method a lot. So one of them is the conclusion, which is where statistics uses analysis, and when we have the experiment for the design of experiment. So biostatistics comes into play in 2 main categories: in the design of the experiment and the analysis. So the places where it comes in design is where we select the sample, whether the sampling is done right, the type of sampling that you're using, all of that is where design comes in. Analysis of that data is where we take unbiased look at the data and then we produce results or inferences from that particular data. So how do we design an experiment? So there is the true experimental design, so which is where subjects are randomly assigned to different groups. We have an experimental group which generally receive treatment. We have a control group where there is no treatment or generally given a placebo. And this allows for testing of cause and effect relationships. And this is critical to control other variables to ensure validity. Now, the last concept is accuracy versus precision. So these are crucial concepts in measuring the measurement quality. So the accuracy refers to the correctness of a measurement or how close is it to the true value. So if you have the true value, how close did you come to the true value? That is measured by accuracy. Precision refers to the consistency of the measurement. So often people, intermingle accuracy and precision, thinking it's the same thing. But accuracy generally refers to being, for example, thinking of it like striking the target at a, let's say, archery range or a shooting range. So the precision is, for example, a person that has to repeatedly shoot the exact same point, but he has to be close enough. So that is precision. So how close the repeated measurements are to each other is what we refer to as precision. So for example, these are 3 visual representations of accuracy versus precision. So here the archer is precise, but he is not accurate, because notice that most of his shots are far away from the target. Only some of them are actually close, but they are not accurate enough. So if a person is accurate and precise, his values are going to be really close to the center or basically at the center, and they are also going to be close to each other. And if they are neither accurate and not precise, he's going to be far away from the target, and he's also going to be far away from each other. So that is what is visualizing the accuracy versus precision. Right? Now, in the recent decades, biostatistics has come a long way, and especially statistical analysis has generally been done through the computer revolution. It has transformed the analysis of data. So computers generally perform these tedious tasks faster and more accurately, and this allows focus more on the interpretation rather than the calculation. So what are some of the common software that's used in biostatistics? We have Minitab, SPSS, SAS, R, and Python. The more common ones that you would have seen are SPSS and R. Python is a programming language, but it can still be used for very good amount of analysis because of the varied amount of Python programming packages that are available for biostatistics. So in summary, what did we discuss today? So we discussed statistics, which is a field concerned with data collection, organization, and inference. We talked about biostatistics, which is the application of statistics to biological or health data. We discussed the two types of variables, quantitative versus qualitative, where quantitative refers to the amount of a particular variable, while qualitative measures the attribute. And we have the two types of quantitative variables, discrete variable and the continuous variable, where discrete has gaps and these are generally result of counting, while continuous are generally present with intervals and they are generally result of measuring. So we also discussed the scales of measurement. We have the NOI, so N, O, I, and R, where N is the nominal scale, which is generally by naming or classification. Ordinal includes the rank, which is not clearly defined hierarchy, but there is a clear rank. So interval refers to equal distance, and ratio has the highest level of information, which is it has a true or absolute zero. And we also discussed the three types of sampling. We discussed the simple random sampling, which is a probabilistic sampling method, where we generally say that everybody in the population has the equal chance of being selected for the sample. We have the systematic sample, which is where if you have the entire list of the population, we generally choose a random number, which is by calculating the systemic sampler k, which is basically the population size by the value that we calculate is k, which is the population size by the sample size. We choose a random number between 1 and k, and then we choose every kth sample from on. Stratified sampling is where we first classify the population into subgroups, and then we do simple random sampling inside the subgroups. So then we discussed the scientific method. So we stated that this relies specifically for statistics on design, for the design, which is the experimental stage, and for analysis to conclude the study. And then we talked about measurement quality. We talked about accuracy and precision. So accuracy representing correctness, which is how close you are to the true value, while precision refers to the consistency or how close you are to each other. So thank you for your time, and I'll come back to you in the next lecture.